Yeah, good morning, students. Welcome to the second module of our system software. Okay, so the matter of discussion will going to be in your second module is loaders and linkers, wherein we are supposed to discuss the basic loader functions, machine-dependent loader features, machine-independent loader features, as well as loader design options, as well as some implementation example, which will going to act as a case study. That is going to be the intention. So some case studies, but these case studies were not there with the assemblers. Even with assemblers, we were supposed to do that, but you have already have experienced with 8086 assemblers, which you have studied. That's why that particular part is not being included. With loaders and linkers, we're going to have some case studies of some real loaders and linkers. That's what's the intention. Yeah. In this, we're going to discuss the loaders and linkers basic functionalities. We're going to talk about absolute loaders. We're going to talk about bootstrap loaders. And in the later on sessions, we're going to discuss about the linking loaders, which is an additional functionality that is added up to your loaders. So that's how the things flow. Okay. We know after we give the source program to the compiler, means we'll look at it in my broader terms. We'll give the high-level programming language source program to the compiler. The compiler does all the 6 phases of the compilation, and at the end, it will go to give us the assembly, reallocatable assembly language. That is, in turn, will going to give to the assemblers of the concerned machine. So the assembler takes up the source code written in assembly language program and converts it into the object program. Now, when it is converted into object program, all the mnemonics will be converted into opcodes, and all the operands would have been converted into addresses. And this is what is the thing. So if we typically look at an object code that is coming as an output from the assembler, it will contain the object program, which is having the instructions in the form of opcode, and the operands, that is variables and constants. Variables will have the addresses, and the constants will have the concerned data values. That will be what your object code file will be made up of. Then what is the task of your loader? The load address, after this object code is ready, we should request the operating system to provide the load address. That load address may be absolute and may be relative. These few things we need to look into. We're going to look into as we proceed. And then your the loader has to do these functions. What are those functions? First and foremost is loading the object program to the memory at the specified load address, which is given by your operating system. This is nothing but, if you look at it, looks complicated, but the things is very simple. Just copy the object program into the specified address. That's what we mean. The loading means copy the object program after assembly to the specified address. That's all is what the loader does. Nothing else. Any loader for that matter is the first task is to copy the object program to the specified address. Later, it should perform the reallocation of the program wherever we have modification bits or modification records we have, or else we have some bit mask. We're going to talk about the bit mask later. So if these things are there, it is supposed to perform the reallocation. Next to say, if we have assembled the source program starting from the address 000, all the instructions and the memory locations, means the operands will be given address relative to 000. But if the load address given is 3000, all these instruction address supposed to be added with the load address, that is 3000. So this is what actually we mean by reallocation. And format 4 instructions wherein the operand will have the direct address, which is not having the displacement. That should be given, but that should also be added with the operand address, need to be added with the load address. These are the things what we'll go to do it in the reallocation. Fine. Proceeding further, we should also do some linking. Linking means the symbols which are defined in other control section but is used in this control section, or the symbols which are defined in this control section might be used in other control section, need to be resolved. Again, this will also happen using modification records, but how exactly that has to be done is what is the thing. But I'll make you sure that all loaders will not do the linking task. It is an option. If suppose the loader doesn't have the linking option, the separate linker need to be invoked for resolving these external definitions and external references. So that's how it works. A loader is a system software that performs a loading function. That's actually the bare minimum or the basic definition of our loader. Means it copies the object program to the specified address by your operating systems. Many loaders supports reallocation and linking, but if not supported, separate linkers or linkage editors will be used. So we're going to see that particular option also later on in machine independent assembler features. Sorry, in machine independent loader features. Okay, we shall start with what we call as the design of absolute loader. So two things we need to see: absolute loaders and relative loaders. Absolute loaders is a bit different from relative loaders. What is the difference? We'll see. The absolute loaders loads the object code in the specified address during assembly. Here this term specified address is mandatory. What do you mean by this? It's not assembled using the starting address 0000, but instead it will be assembled by the address relative to the address which is specified by the program. Suppose at the start of the program, users has specified something like name of the program start and 2000. Means to say the first instruction address starts from 2000 and all other instructions relatively get the addresses starting from 2000. Maybe if it is 3-byte instruction, to next instruction will be at 2003, say 4-byte instruction, next it will be at 2004, so on. I think hope you all can make it out. So based on the size of the instruction or based on the size of the variables in the constant, the addresses are assigned by your location counter during assembly using the starting address which you have specified with the program. So this sort of example we have solved when we did our SIC program during assembly. I told you that this is an absolute assembly, means we are specifying the addresses exactly. This is the address that you are supposed to, like 1000 or 2000, and all the assembly will going to be done like that. The problem with this sort of code is this program could be executed if that specified address, for example 1000 or 2000, is available while you are executing the program. If not available, that program could never be executed. Then you may ask me that what is the need of this absolute address? Yes, of course, we may need some absolute address. For example, when you start your machine, the operating system should be loaded first. Operating system should be loaded. I'm using the word loaded, right? So there should be a loader there. When you start your machine, the first thing to get started is your BIOS, basic input output system, which is going to perform a task called as post. It is called as power on self test, which is going to test all the components attached to your system. Means all the hardware components are there or in a working state. So that test will be done, and immediately after that, you may get a beep indicating that yes, everything is right, checked. Once after this, what is going to happen? Your basic input output system will go into load a loader, which we call it as a bootstrap loader. The bootstrap loader will be, the bootstrap loader's address will be known to your BIOS. So it will just go to that address and we're going to bring the contents and put it on the top. Usually it will be there in the 0 sector, 0 track, 0 cylinder of your hard disk. So that's why when we usually install our primary operating system, we're going to choose a C drive for installing that. The reason is it will going to be given in the boot sector. Boot sector will be used for installing or storing your bootstrap loader. Once after the bootstrap loader is loaded, your bootstrap loader in turn will going to load the operating system. So your bootstrap loader should exactly know the address of bootstrap, means your operating system, and should bring it to the same address. It should bring it to the specific address. So that's where the absolute loaders come into picture. The absolute loaders doesn't have any significance. with the user programs, whatever we are running. Is try to understand the overall concept. So that is going to help us. So, but anyway, we shall see the design of the bootstrap means absolute loader, then the bootstrap loader, and then the rest of the loaders. Okay. No linking function is to be done because the address is predefined. So you are supposed to load the content onto this particular location. So that's what is your absolute loader does. Entire task of absolute loader done is one pass. There is no much task. Just the copying of the contents of object code to the specified address. That's what is your loader is doing. So they can be performed in only a single pass. How it does? It check the header record of your object code. And from the header record, we can get two information, the start address as well as the size of it. And we should see whether the size of the program whether the program fits into the memory which has been allocated. So the size of the size can be got from the header record. We're going to check whether that entire program can be loaded in the memory allocated to us. If yes, then what is the next step is read the text record from your object code and move it to the specified memory address. That's all. Just copy paste. That's what is your loader is doing to the specified address. Until you get the end record. Once you get the end record, it jumps to the starting address of that particular program and starts execution. And the execution will be started later. So the loading work will going to be completed. So at the end of every loading, after the program is completely loaded, the loader should point to the first executable instruction. That's what is the task, how your loader will going to work. And in the example, we're going to see next. Wherever there is XXX, it is indicating there is no text record. Means it is a blank. It's blank. Don't need to worry about it. We shall see two examples for this. This is one example, a simple program here. What this program is doing is, it is copying the contents of alpha to the contents of beta. Means with adding it with, means it is going to add the contents of alpha with beta and store the result in sum. We shall see step by step. And you can see the first row, it is been specifying ARTH, which is the name of the program, followed by start, followed by 1000. We are specifying an absolute address. We have not given 000. And the first instruction of your program in the row 2 is telling load accumulator with contents of alpha. Then next instruction is telling add contents with of accumulator with beta, and the result will be stored in beta. Sorry, result will be stored in accumulator, and store accumulator contents to the sum. And we have three declarations: alpha, beta, sum. Alpha is a word which is a constant whose value is 4. Beta is a word which is a constant, integer constant, whose value is 2. We have not declared them as a variables. Means to say we are just doing 4 plus 2. Our intention is not about writing the program. Our intention is to understand about how the loader works, with the absolute loader works. So the sum is a integer variable of size 1, means it consumes 3 words. So you can see the location pointer values. First instruction LDA starts at 1000 because the start address is 1000. Next one is 1003. Next is 1006, 1009, 1000C, because everyone is consuming 3 bytes. Roughly means they are consuming 3 bytes. One at 100C, next is 100F, and your end is falling at 1012. This is the problem. When we give this to the assembler, assembling is done. You please pay attention to the object code at the rightmost column of your table. You can see there that is the first one is 001009. I can make it. You can make it up. It's a simple SIC program. 00 is the opcode of your LDA. Then add opcode is 18, and beta's address is 100C, and sum STA's opcode is 0C, and the sum address is 100F. And anyway, alpha and beta are constants, so simply it is been mentioned. Its value is 004 and 00. Fine. When after assembly, when this is written into the object code file format, it looks something like this. It is containing a header record H, name of the program ARTH, and then start address is 1000, and it is specified in 6 bits. That's the difference. You can see that 001000 is the start address, and 0012 is the size of your program. Fine. After that, we have text record. In this text record, we are having start the text means the object codes starting from 00100 till 0F. That much text records we are accommodating in this text record. Yes, only we have hardly 5 text records, hardly 3 text records. That's all. Okay. First one is 00109 and then 18100C and then 0C 100F, and the constants is also been mentioned. And the end record is also again starting and specifying the start address from there where the execution happens. This will be the outcome what we get after the assembly. Now we shall give this to our what you call absolute loader. Your absolute loader should copy these 3 object code to the address. Which address? Starting from 1000, 1003 and so on. Right? Like that. So this what will happen. You can see the symbol table entries. Alpha is present at the address 1009, beta is at the address 1000C, sum is at the address 1000F, and starting from the address 1000, we have loaded the object code, which are the 1009, 18100C, 0C, 100F, and also the constant 004 and 002. That's all is the work of your absolute load. Convinced? Fine. And usually will not be asked to write an example program and explain the design of absolute loader. Actually, there is an algorithm. Whatever I am showing is not exactly correct. We're going to modify this. I use this example so that we can understand the working of the absolute loader. But exactly how it actually works, we're going to see it later. Please don't use this example. It's not required. You will be asked with the algorithm and the working. We shall see that the actual textbook example. This is a textbook example. We are given with an object code. Don't worry, this is just an object code. The name of the program is copy and it is starting with the address 1000 and 107A is the length of the text record and this is the all of the text record. And you can see the end record. End record is again pointing to 1000, means your first instruction start execution should be is present at 1000. Okay, right. In exam you don't need to write this much code. For that I have given this example. So we simplifying. If it is asked to explain how the design works, if it is asked the algorithm and this thing, you can do it which are there next. Fine. Okay. Yeah. If after loading your program looks like this in your memory. See, we are starting with the address 1000. At 1000, we have the first text record being placed 14103348. You can see that the first text record at in the second row. You can see there after 00100 and 1E, which is the start and the size, we have 14103348. That is placed in first what you call means at the address 1000. The next set of text records are being placed in a consecutive locations. Means this is the task of your loader. It just copied the contents of your text records from your object code file onto your specified address. As it is an absolute loader, it's supposed to allocate, means it's supposed to load this onto the address starting from 1000. So it has did. And you can see after during the some locations in 1030 are marked as XXX. Means there we don't have any what you call text records. It is blank. And you can see there's from 2040 the next set of text records are being allocated. Right. So this is what we call it as absolute loading. Right. And here one thing we need to understand. We have an algorithm for absolute loader. What is the algorithm? Just see that. We can read the header record. Yeah, you read the header record. From where you will get the size of the length of the program. Verify the program name and the length. Okay. Why you are verifying? So as to confirm that the program can fit in the allocated memory location. That's it. Okay. And read the first text record from the object code file. And until the text record is not equal to end, we should repeat this thing. What is that? If the object code is in a character, please understand this. This is the important thing that need to be understood. If the object code is in a character form, convert it into an internal representation. Convert it into an external, means internal representation. What that means is, by default, your object code will be in hexadecimal format. But while loading, your loader will compress your object code. Means to say, whatever the previous example we have seen is also not correct. It's not true. So we'll convert it into some form called as hexadecimal character representation. What that means? Each hexadecimal character occupies 8 bits or 1 byte. But while loading, it will be shrunk to half. It will be shrunk to half. Means within 1 byte, we are going to represent 2 hexa characters together. 2 hexadecimal characters together. This will going to save our space when we are representing our opcodes. So that's what is it. We have an example that follows. We are going to see that. If the object code is in character form, convert it into an internal representation. This is what is the very important task that will be done by your loader. Till now we haven't specified this functionality. The loader converts it into a hexadecimal character representation. That's what we mean by internal representation. Means you need to broadly understand that whichever used to consume 8 bits will be shrunk to 4 bits. 1 byte will be shrunk to half byte. That's how is the thing. After this is done, move the object code. Means this you should remember, because the same concept will be again applied for the bootstrap loaders and other loaders also, because this you may get confused that why we are just doing these comparisons and shifting and all those things. That we're going to be able to understand if at all we have understood this. Okay. Once after this hexadecimal character conversion or representation or internal representation is done, we'll move the object code to the specified location in the memory. Read the next text record, read the next text record until when? Until we have reached the end record. Once after this end record is encountered, see that after the while loop, we are jumping to the address specified in the end record. Which address? The starting executable address. That there we're going to jump. This is the design of the algorithm for implementing the absolute loader. Very important things, very important one which will be asked many times in the examination also. And you are supposed to explain this internal conversion representation also. Fine? Yeah. Converting object code to the internal representation. We are going to see each character in the object code occupies 1 byte according to our ASCII representation. Fine. During loading, we use this character representation where each character consumes only half byte. Half byte, that means 4 bits. How is it done? See this example. Example, we have somewhere written STL. The STL opcode is 1,4 hexa. Correct? No? So 1 consumes 8 bits, 4 consumes 8 bits. Totally, so as to represent the 1,4, we need 2 bytes. But while loading, this will be converted into only 1 byte. That means 1,4 is taken as a value, not 2 bytes. 1,4 is taken as a value, not as a 2 bytes. But this didn't happen with your assembler. Your assembler also allocated 8 bytes for your representation of the output. Fine? Okay. Yeah. But in character representation, 1,4H is stated as a single value which is consuming together. 1,4 together is consuming 8 bits. Right? This is what we call it as converting the object code into an internal representation. Fine. So this is the design of the absolute loader, wherein or this may also be asked as basic loader functionalities, right? Either as a basic loader functionality or as a design of an absolute loader. Mandatory thing is you're supposed to write about the algorithm as well as explain how it is going to be converted into an internal representation. So the internal representation is nothing but 8-bit will be converted into 4 bits, or the entire value will be converted into a single value, so that or single character or single value. Fine. This is about what do you call absolute loader. The next loaders we're going to see is bootstrap loaders. The bootstrap loaders, name itself indicates, it helps in booting time, right? When a computer is started, a special type of absolute loader, bootstrap loader is by default is an absolute loader. It's not a relative loader. It will be started. Who will start that? Your BIOS will going to start your bootstrap loader, which will going to be which will going to in turn load the operating system. The loader is responsible for loading the startup routines, that is your operating system. Right. The bootstrap begins at address 0 and loads the operating system to a specific address here. Here in our example, we are assuming your operating system is supposed to be loaded into a address called as 80H. Means your operating system will be loaded consecutive location starting from 80H. This is a standard what we are assuming. So it's not required that every operating system will be loaded onto 80H. But for our example purpose, we are assuming that it will be loaded onto 80H. Right? So these few assumptions we need to be clear so that we can proceed further. Okay. Each byte of the object code is loaded from the device F1. Here the F1 is an input device that's not required to be a keyboard or a mouse. It can be your secondary storage device, hard disk or whatever it may be. From that device, from the device F1, hexadecimal unique code for your device is F1. From the device F1, we will be loading the operating system, right? And then the object code is loaded into consecutive locations starting from your 80H. And as your start address is 80H, your execution will also start from 80H. Right? We shall see the example program. So that is going to make us to understand this particular concept of bootstrap loader. Yeah. Before going to that, we need to have these values or these assumptions ready. What are those assumptions is decimal value 48. How can I differentiate between decimal and hexadecimal? In your program, if at all some value is taken as hash and a value, means in an immediate addressing, that we are going to take it as a decimal. Please understand, if some value is prefixed with a hash, means if we are using immediate addressing, we are using that as a decimal value, right? And that internally means something else in hexadecimal. Okay. So 48 means ASCII value 0. That means ASCII code for 0. Okay. And in hexadecimal representation, its value is 30 hexa. Similarly, 49 to 57 represent 1 to 9. Okay. And which is represented in hexa as 31 to 39 hexa. This looks a bit confusing. But after we have seen the example, the things will going to be better. 58 to 63 is representing A to F, right? 41 to 46. And apart from this, we have some constants. For example, 80H in decimal, 128 in decimal is representing your 80H. Means somewhere if we have hash 128, we should assume that as 80H, which is your starting address, where your operating system is supposed to be loaded. And the end of the file is represented by 04H. Means anything less than or equal to 04 is a end. Okay, less than or equal to 04 will going to be an end. Why we are using this? Please observe, when we write an SIC or a SIC-XC program, a program will be made up of object code, means the program will be made up of mnemonics and operands, correct? So you're going to either have addresses or either have hexadecimal equivalent port format. Your hexadecimal may contain the value starting from 1 to 9, correct? And A to F, hexa, correct? Apart from this, you don't get anything else in your program, isn't it? We don't get any other if or else or any such sort of thing. Your entire SIC or SIC-XC program is made up of 1 to 9 A to F, either the addresses or it may be the mnemonics or maybe anything. Will going to be either of these things. Mnemonics, operands, or means mnemonics and addresses, everything will going to come in hexa. Hexa is made up of 1 to 9 and A to F. So apart from this, 0 is treated as 30H, End of the file has a special rotation 0 more. And the starting address, we are having 8H. So these many hexa values we should be knowing. So as to load this particular operating system into the memory, into the location 80H. Okay. So it's time of warning. So we shall start here, and we're going to continue with our what you call bootstrap loaders in the next class. Fine. So example and implementation and algorithm, we shall see it in the next class. Fine. Thank you. Thank you for joining.